I'm late. I had a very busy day, and but I think we can still do it, so no problem. We're gonna go from now till 7 o'clock sharp, and then we'll take like a 10-minute break, and then for the lab we'll start at 7:10. But we should be able to finish what I had in mind to do. So some announcements, if you don't mind. I did post the group numbers, so everybody should know which group they are in. So Thursday we have group 1, 2, 3, 4, I believe. Friday we have group 1, 2, 3, 4, or Saturday 1, 2, 3, 4. So these are the groups, and you have your numbers now. You should know your numbers. Okay. If somebody doesn't know for sure, please ask me tonight. So because you're supposed to be working on your projects by now. All right. So let's see. I also posted this lecture again. So I would like just to show you what I did. So these are the same. The new things I did is just very much. I showed the slab here with the dimensions, and then I showed the girders, girder 1, girder 2. With the reactions coming, but the most important thing is I showed this table, and this is gonna help us calculate how deep is the slab, because somebody had a question, how did we calculate the depth of the slab? It came from here, and I'll go over that. And then also the beam, when we did the beam analysis for the DT beam, we had to assume the beam section. So how did we do that? This came from this table, and then I will go over that and show you. So those are new slides. This is new. We also gonna learn how to design the column, to size up the column. And then the rest, let me see. The rest are the same. Yeah, these are the only things I did. All right. So we're gonna do that today, and we also are going to do the continue chapter 2. So let me go to that. McCormick. Okay. So let's see. We did get this far. Yeah. So we did do this example. Did we do example 2.1 for the cracking moment or not? Anybody?
No, we haven't done that yet.
We haven't.
No.
Okay. All right. So that's where we're gonna start. We'll start with that then. So let me finish this chapter 2, and then we'll go back to the other stuff, talking about the slabs and the beams. All right. So last time, very quickly, we talked about the cracking moment formula, how we get that. Right? We did do this, right? Anybody?
I don't really remember doing a cracking moment formula.
All right. So let's start from the cracking moment then. Let's start from the cracking moment. All right. So we said that the beam is going to crack on the tension side, as you can see here. So we want to know what moment does it take to crack that beam, and that moment we're gonna call it the cracking moment.
Professor?
Now remember, we said initially when the beam is sitting there, the steel is sitting inside the beam, and then the load is small. The beam is gonna deflect, and then there will be tension on the bottom and then compression on the top. We talked a lot about that, and very important you understand that, please.
Professor?
Okay? Yes.
I think you still have the project PowerPoint.
I'm sorry. Yes, we have to do a new screen. Thank you. Yeah, please always remind me. Okay, can you see it now, the cracking moment?
Yes.
Okay, thank you. Yeah, please don't hesitate. Remind me. So we said that last time. Remember we said tension on one side, compression on the other side, and then right here we looked at this. So this is where the crack's gonna go at the tension side, and we said that the crack's gonna start at a value of moment right here, which we call it M cracking. Because when the moment is small, there is no cracks. Why? Because we haven't reached to that stage yet where the beam cannot take any more tension. So we call that cracking moment. All right? So how do we calculate that? So this is the formula. But like I told you before, we're not going to blindly apply formulas. I'm going to tell you exactly why and where it's coming from. This is the very, very important formula we studied in strength of material or deformable bodies, which really, if you have a moment applied to a beam, you can calculate the stress on that beam. Stress equal M times Y divided by IG, the gross moment of inertia. Okay? Again, M is the applied moment, Y is the distance from the centroid, or like almost half the beam to the top or bottom, and IG is the gross moment of inertia. The only thing about this formula, and I mentioned it probably last time, and I'm sorry, I bet you we all missed it in strength of material. This formula can only be used for homogeneous beams, meaning that if your beam is made out of steel, structural steel, you can use this formula. When your beam is made out of wood, you can use this formula. But when your beam is made out of concrete only, you can use this formula. But the minute you mix concrete and rebars, becomes reinforced concrete, this formula no longer applicable. Okay, and you will see how we're going to get around this to calculate the stresses in a reinforced concrete beam. But now, since I'm calculating the cracking moment, meaning my load is small, it's just going to get high enough so that the tensile strength of the concrete is exceeded. Well, before the tensile strength of the concrete is exceeded, even if you have bars laying there, they're not doing anything. They're just waiting. They're just waiting for the stress to exceed the cracking or the tensile stress of the beam. Then they will be activated. So even if the rebars are there, but they're not activated, it's considered homogeneous. Because yes, they exist there, but they're not working. So we're going to consider it as a homogeneous concrete beam. So because of that, I can use this formula. See that? So now if I cross multiply, M is equal what? F times I divided by Y. So there you go. This is the formula. Now I'm going to call that M as the cracking moment. Now, this cracking moment is going to happen when the tensile stress of the concrete reaches FR, right? Which is this value right there. Where's the value? Let me see. Right there. This is the tensile strength, the cracking stress of the concrete. When the tensile stress of the concrete reaches this value, then the concrete will crack. So what I'm going to do, I'm going to replace this stress with F sub R. IG is constant, it doesn't change. YT is constant. Y is the distance from the neutral axis to the top or bottom. But then my M becomes M cracking. All right, so this is the formula we're going to use. And you will see very simple to use. First homework actually will be on this. So how do we multiply? FR is equal to this. YT is the distance from the centroidal axis to extreme tension fiber. See, that means the bottom. Extreme tension fiber at the bottom. If the tension is at the top, then it's the top. So again, this is F sub R, and we said lambda is 1 most of the time. If it's a lightweight concrete, then it's 0.85%, lightweight 0.75 for that. Most of the time in this course going to be lambda 1 because we do normal weight. So let's do the example and see how easy it is. So there's the beam. We're given a beam. The dimensions are 12 by 18. See, when we did the DT beam, I assumed my beam was, I forgot what it was. I assumed 12 by 18, whatever the number is. So today I'm going to show you how we estimate that depth from that table, okay? We'll get to that. So I'm given a beam 18 feet deep 18 inches deep, sorry, 12 inches wide, 3 number 9 bars. Now 3 number 9 bars, we're gonna start doing this now. If you go to the back of the book, you will see a table where you can find what is 3 number 9 bars, what is the area of steel. Okay, it's gonna be 3.0 inches square. And of course, we cannot put the rebars at the bottom because we need some concrete to go underneath to provide a cover for it, to protect it from moisture, salt, wind, all the environmental impact. So we do that cover. This distance is either 3 inches or 2.5. It's not going to be anything different. Either 2.5 inches or 3 inches. All right, depends on the bar size, and we will look at that. And then, so if this is 18 and this is 3, what is this left? 15. And then again, this is from the center line of the bar to the bottom. So that's all given. He's asking me for the beam shown in the figure, compute the bending stresses for a moment of 25 kips foot. So if a moment applied to this beam, 25 kips foot, what are the bending stresses that we can do? Use normal weight concrete, 4,000 psi. Modulus of rupture is 474. This is the F sub R. F sub R is right there, is modulus of rupture. Okay, so that's given. And determine the cracking moment. What is the cracking moment? First of all, look at this. It's saying compute the bending stresses for a moment of that. What is the bending stresses? This is the formula. F is the bending stress equal my over Ig. So what is the bending stresses? Let's do that first. So calculate the bending stresses assuming the section uncracked. Why do we do that? Because look at this. Look at the formula again. I say I gross. That means the gross moment of inertia of the gross section. Okay? This is the case when the beam is uncracked. When the beam cracks, look what happened. When the beam cracks, you think the moment of inertia for this section with these cracks is the same in this area where the beam is not cracked? No, it's not. It's much less. It's much less than that. Okay? And there's a way to take that into consideration. Later on, we'll cover that. But so for now, we're going to assume it's uncracked, and we can use the gross moment of inertia, which is BH cube over 12. So what is that? See that? Calculate the bending stresses, assuming the section is uncracked. Since I assumed that, I can then Ig is this. My full section is working. Ig, the gross area, BH cube over 12. B is 12, and H is 18. See that? This is always B. H is this, and then 15 is D. We always call it like that in per ACI code. So if you substitute, be careful with the units, then you're going to get this number inches to the power 4. All right? Now, so he's asking me for the bending stresses. What is the bending stresses? This is the formula. I just plug in here. So the bending stress is my over Ig. M is 25. He gave me 25 kips foot. So watch for the units. So we're going to multiply by 1,000 to get it in pound foot. Y is 12 inches. 12 inch per foot to get this unit from feet to inches. All right? And then what is Y? 9. Why is that? Because we said Y is half of the beam most of the time. So 18 divided by 2 is 9. Divided by I is that. So look at the units. This is inches to the 4. This is inch. This became pound inch. So your answer is PSI, pound per square inch. Okay, so that's your. So the bending stress in that beam due to this moment is 463 PSI. Now, where is that stress going to be? At the bottom of the beam. That stress is going to be right there. Right? That stress is going to be right here at the bottom of the beam. Why? Because the beam is deflecting like that. The beam is deflecting like this. So the maximum tensile stress is going to be at the bottom. All right. Now, we can use the same formula to determine the maximum compression stress at the top. Same formula, okay? So we'll talk about that later. All right, so we got that. So it's 463. Now look what the problem told us too. The problem said that the modulus of rupture is 474. This is a stress too. See that? This is a stress, PSI. Look at that, F is a stress, R is for rupture. So this is a stress. So the modulus of rupture for that beam is given as 475. What does this mean? This means that when the tensile stress in the beam gets to this value, what's going to happen to the beam? Anybody? When the tensile stress in the beam gets to this value, what happens to the beam?
The ruptures, the breaks.
It's going to crack, yes.
Yeah.
It's going to crack. The minute the stress is going to get to this value, it's going to crack. All right? When we reach this, we're going to see this crack right there, starting from the bottom going up. Okay? So that's what happened. So if this is the cracking stress per se, and then I just calculate my stress is 463. 463 versus 474. You think the beam cracked or didn't crack? Anybody? Did the beam crack?
No.
No, it didn't, exactly. Because it takes 474 to crack it. My moment only gave me a 463. So the beam did not crack. And I usually ask that in the exam. I give you a problem and I ask you, did the beam crack? You have to compare those. See, the problem didn't ask for that. But I'm just saying that so you understand. It says determine the cracking moment. So what is the cracking moment? All right. So we got the actual tensile stress. And now we will calculate the cracking moment. So what is the cracking moment? FRIG over Y. Came from here. I'm cracking FRIG over Y. So here he's listed as FR times section modulus. So don't worry about that. You will see section modulus in steel when you do steel design. But we don't need it at this time. So it's equal FRIG over Y. FR is what? This is when it's going to crack, so it's 474. That was given in the problem. It's telling me the tensile stress when the beam is going to crack is that. So I put that in, and then IG I calculated, and now Y is 9. So that's going to be, M cracking is going to be 25.6 Gibbs foot. All right? Now, let's look at the number. So here and like I said, always judge your numbers. This is telling me when the applied moment reaches 25.6 Gibbs foot, what's going to happen to the beam? It's going to crack. What is my moment? My moment is only 25. So did my beam crack? No. See, we showed it both ways. My applied moment is less than my cracking moment. So the beam didn't crack. And my tensile stress in the beam is less than my modulus of rupture, which is the stress, so my beam didn't crack. See that? This way you understand what's going on with the beam, not just applying the formula and, oh, this is the modulus of rupture. We don't know what it is, but this is it. So you got a feel for that? Any question on that? All right, so this is the example. I'm going to assign a homework, very similar, different numbers. Different number, guys, so you make sure you don't miss any homeworks. And I'll do a drop box for it so you can drop it and I'll give you the delay. Usually I'll give you a week to do so it's due by next Thursday. Any question on that? All right, so we know how to calculate the cracking moment now. All right, so now elastic stress is cracked. From here on to, please, I'm going to skip that. So anything with an N, we're going to skip that. If we have time at the end, we'll come back to it. So skip this. Look at the small N here. And then there's reasons for that. I don't want to confuse you with it now. Skip this example. So skip 2.2 for N. Skip all that. I leave it intentionally so when you are reading in the book, you don't say what happened to these. I'm telling you, we're skipping those. We're gonna skip all that until we get to, we're gonna skip the double reinforced beam for now. We'll come back to it. Skip all that until we get to here, the ultimate load. All right. Now, remember what we've been doing so far is we started with a small load, we increased, and we went from elastic to inelastic and all that. The ultimate load is the load at which the structure is going to fail. What's going to happen when the structure is going to fail? Of course, we don't design our structures to fail, but it's going to fail in case of something, an earthquake or somebody overloaded it, like the example I gave you before. So what is the ultimate load? So remember this stress and strain a while ago, they used to be linear like this, right? They used to be linear. And let me just quickly, sorry to remind you that because it means a lot to you. You'll see, so you don't, we'll be very quick. Remember we started here uncracked stage. The stress and strains were small, elastic, linear, no problems, okay? Then the load increased a little bit more, the beam cracked at the bottom. What happened? All the concrete below the neutral axis we ignored because the steel picked up the stresses. So look what happened with the stress. We ignored the steel stress, the concrete stress, and we replaced that. We just put the steel in, the stress in the steel. But then look, the compression stress remained linear because my load is small. Okay? So now, again, we did that. Now when we go to ultimate stage, then my compression stress no longer gonna be linear, it's gonna be a parabolic like this. All right? And why is that? You will see because it follows the stress strain curve for the concrete as a material. All right. So that's where we left off, and we're going to continue that from where we left off. Right there. Okay. So we said that the stress is going to be parabolic like this. All right. Now, why is that? This is what I told you, sometimes analytic we can solve, but sometimes we need the experimental. The experimental is this. Remember at the beginning we said the stress strain curve for concrete is this. When you start loading it from small load all the way, it goes linear. As the load goes up, stress goes up. Ultimately it does this, and then it fails. So it's parabolic. So it's obvious that when the load is high, your stress and remember this is the compressive stress. The compressive stress is going to be parabolic at higher loads. That's why this is how it's going to look. Okay. Now coming to this, what is the maximum value from here to there? That's the F prime C. This is the F prime C, the compressive strength of concrete. So I come here, there's the maximum value. So look at it as if you rotated the curve. The maximum value is F prime C. See that? This is what is stress at ultimate load. This value is coming from right there. All right? Okay, and then of course, what is the epsilon here? This is the strain. This is the epsilon of concrete at the top in compression. And then this is the epsilon of steel in the steel bars. Notice that we dropped this long time ago because we said the concrete cracked, so it's no longer there. So I have an epsilon S. At ultimate load, you will see we're going to design it so that the steel is going to yield. It's going to yield. And we showed that last time. That means that the epsilon, the stress in this, the strain in the steel is going to be epsilon Y. Okay? And why do we want it to yield at higher load, at ultimate load? Because when the steel yields, and think of it as it's getting stretched. When the steel gets stretched, guess what's going to happen? It's going to sag, right? Think of it as smelting slowly, it's gonna sag. So we want the steel to yield at ultimate, because if the steel yields, it's gonna sag, the beam is gonna sag, people are going to notice it. You think they're gonna remain in the building or they're gonna run out? They're gonna run. They're gonna run out as quick as they can. So what the code is saying that we want to design the building such that if it's unintentionally loaded by like the example I gave you, when they stack the bags of cement, or when a quake hits and the building cannot resist that and the building is gonna fail, we want some warning signs. We want warning signs so the people can evacuate. And that warning sign can happen only if the steel yields. So then the strain in the steel, I'm going to set it greater than or equal. We will set it equal to the epsilon y, the yield stress. Okay? We will talk a lot more about that.
Oh, Professor?
Yes.
Can you just explain the difference to me again between the epsilon y and epsilon s?
Yes, no problem. No problem. Please ask any questions as many times as you like. The epsilon s is first of all, let's start with the epsilon c. This beam is getting loaded. It's going to be tension at the top, compression at the bottom. And we will continue repeating that forever. If there is a compression at the top, that means there is a compression force, and the force yields to a stress. Why? Because the stress equal force divided by area. And the area usually is constant, or we know the area that the force applied on it. So we know there is a compressive stress and gives us compressive strain. How do we get from stress to strain? We know from strength of material, stress equal E times strain, right? As stress equal modulus of elasticity times strain. So we can easily get either, stress from strain or strain from stress. Well, once we know modulus of elasticity, and we know the modulus of elasticity because it's a material characteristics. We said for concrete is 57,000 square root of F prime C. That's the epsilon C. What happened at ultimate? Remember, the beam is cracked below the neutral axis. So we ignore the concrete. So who's picking up the load? The steel. The steel, we said, is good in tension. So the steel is going to have a force in it. And the force is going to lead to a stress and a strain. Again, F equal E times epsilon. Now, the E here, the E we're going to use for the steel is not the same as the E for the concrete, because the E for the steel is 29,000 KSI. Different than that. Depends on the material. Again, we're going to see it a million times. So I have a stress in the rebars and I have a strain in the rebars. The strain in the rebar, we're going to call it epsilon S, because strain S is for steel. Okay? So we know what epsilon C is, strain in the concrete in compression. Epsilon S is the strain in the steel in tension. But the code tells us that we want you to design your beam at ultimate, if it's going to fail, such that the strain in the steel is equal to the yield strain in the steel, which is epsilon Y, right? Because we want it to yield. So you set epsilon S equal epsilon Y. Is that clear now?
Yes, thank you.
Okay, you're welcome. And you will see how we calculate epsilon Y very easily later. Because the code tells us to do this, and you will see later why we want this to happen. We'll get more chances to explain that. So it tells you strain at ultimate load, meaning at failure load, we want epsilon S greater than or equal. To solve the problem, we set them equal epsilon Y, And we said this came from here. Now, let me skip this, I'll come back. If this is my stress, right? So this is my compressive stress in the concrete at the top. And this is my, let me say this. This is my compression force, first of all, at the top. And this is my tension force in the steel. See, we call it T. See that? T is for tension force. And then in a little bit, we're going to call that a compression force pushing on that. Let's look at the T first. T is in tension. Again, stress equal force over area. Force equal stress times area. See that? The area is the area of steel, the area of this bar, because this is what we are stretching, is the area of the steel, is AS. And like we said a minute ago, it's very easy to know that 3 number 9 bars is 3 inches square. And then the force equals area times stress. It should really be AS times FS, right? But we replaced FS with FY because we want the steel to yield. So we replace it with F sub 1. Is that clear? So here we said we want the strain to be epsilon Y, and the same thing we want the stress to be F sub Y. So that's the formula. All right. Now what happened on top? There's a force here, and let me get the pen. So really, there is a force applied here. And let's call that TC, compression force. Right? Because the beam is bending, there is getting stressed at the top, tension at the bottom. So there's a compression force at the top and a tensile force at the bottom. Now, this beam has to be in equilibrium. That means it's stationary, it's fixed in its location, it's in a building. It doesn't move. So we have equilibrium here. If I have equilibrium from statics, summation of forces in the x direction equals 0. Otherwise, if it's not equal 0, the beam is going to move. So what are the forces I have? C and then T. Look at this. Plus C minus C. So you can tell C has to equal to T for equilibrium to happen. Okay, T is easy to find. AS times Fy. How do I calculate C? See how, guys, we are deriving the equations. The equation is very simple, but I want you to understand the mechanics. How do I calculate the C? From calculus, right? Calculus 1, we know that the area under the graph is equal to the force here, right? This force equals the area under the graph. How do I calculate the area under the graph? I need to know the equation of this parabola function. Is usually fx is x squared plus something, right? That's a parabola. I need to find the equation of this curve and then integrate that. Take the integral of it between 0 and this point, 0 and C. That gives me the area under the curve. But is that easy to do? No, it's not easy to do in design offices. So we need to find a simplified solution for that. All right? So an American engineer in the early 1900s came. His name is Whitney. He came and said, okay, instead of doing this, I'm going to convert this to a stress block. So he's going to, because this is parabola, he's going to convert this to an equivalent rectangular block. Because if I do rectangular, and then my C now is easy, right? My C is the area of this rectangle. Can I calculate that? Yes, easy. So what Whitney said that the constant concrete compressive stress is 85% of ultimate stress. So he said, take this compressive stress as 0.85 of F prime C. Although look here, it's F prime C. He said, no, take it 0.85. And then let me grab the pen here. If you draw this line, it doesn't match this time. I just wanted to show you the gap here, okay? So this is that. And then remember, C is now going to be here. All right? So C is going to equal to the area of this rectangle, which is very easy. So Whitney said this dimension is 0.85 F prime C. No problem. Whitney said this dimension, look at C is from the neutral axis to the top. Whitney said this distance is less than that. So we have to multiply it by a factor called beta 1, has to be less than 1, right? Beta 1 has to be less than 1 to be able to shrink that. So he said if we take 0.85 f prime c and this dimension is beta 1c, then we can calculate that. So we will see what the beta 1 is and what c is, and then we can calculate that. Any question on that? Any question? All right, so this is that. Let me erase this so we can... all right, so that's that. So Whitney said is 85% of the stress block, and then rectangular stress block extends beta 1 times C. That's what beta 1 times C. All right? Now, beta 1 depends on the strength of the concrete. Let me skip to that. See, beta 1, if F prime C less than or equal 4,000, which 99.9% of the time is going to be that way in the class and in the real life, beta 1 is 8.85. 0.85. So another word is beta 0.85. So this dimension is 85% of C. And this dimension is 85% of F prime C in plain English. All right? So that's what Whitney said. All right. Now let me just make a couple of side comments here. So this guy, Whitney, came up with this very big simplification. Otherwise, you know, how you're going to find the force here, you know? How did he came up with that? You can tell he did something like this and he went and he's tested it experimentally to show that this is really equivalent. This is equivalent to that. And look at this. This is in the early 1900s, right? This is still valid till today. With all the technology, with all the research, nobody can prove him wrong yet. Nobody can prove him wrong. And then I want to say another side comment here. Some students ask, you know, later on, and I was in the same shoes when we were in the undergrad. Okay, I want to go to a graduate school. Okay, you get a master's degree, no problem. But what about a PhD? What's a PhD? How do you get a PhD? Because, you know, the master is only classes. You could do research. You don't have to do research. It's optional. But the PhD, you have to do research. And you have to come up with something new that nobody came up with it before. I mentioned that because this is a perfect example to illustrate that. This guy, Whitney, came up with these. And then he proved them in the lab it works, and we've been using it for all these years. If somebody can come here now, and prove that this is not correct, and he can come up with new numbers here, new beta 1, and new this 0.85, and prove it in the lab or analytically and all that, he gets a PhD for that. See that? This is what a PhD is for. They want you know, you take a problem where there are assumptions made to solve the problem. If you can release some of these assumptions and prove what they are, then that's a PhD. Just to keep it in mind, because I know I was in your shoes and we didn't understand how do I get a PhD, what do I have to do and all that stuff. So this is a perfect example. If somebody can prove that these can be modified and give us better results, that's a PhD topic. All right. All right. So for now, this is what we will use, of course. All right. Let's continue. So this is again we got beta. This is the 4. Now, if F prime C is greater than 4,000, beta 1 is this is the formula for it. So all you have to do is plug F prime C here and then solve for it. And then, but no matter what this value is, it has to be greater than or equal to 0.65. Like I said, practically speaking, this is going to be your number most all the time. All right. So what else we know? We know the concrete is assumed to crush at 0.003. Remember from the strain diagram? We said the concrete is going to crush here and crush there, but we said we will assume that it breaks at 0.003. Remember that? We did it when we did the first chapter. Replace non-linear variation of stress with the witness stress block. So we're saying replace this guy non-linear with that. And we can solve the problem, and you will see how we do it. So now here you go. We are back here. So we replaced this parabola with this, and let's solve that. There's my 0.85 f prime c. There's my c from the neutral axis to the top. But this dimension here, which we called it beta 1c, we're going to call it A. We're going to call that A. Okay? We're going to call it A. Okay, A equal beta 1c. So you come here, there's A. A is the depth of the we're going to call it compression block, stress block. The width is 0.85 f prime c. And then this is the force. This is the C force, compression force. The compression force is to replace this, which is going to be the resultant of that. Remember from statics, resultant of this load, we're going to do it as one force. What is that force equal? The area of this rectangle. So the area is C equal 0.85 f prime c times A. Okay? So that's the area. See how easy it is now? Now, but this force is applied along the width of the beam. So we have to multiply by B right here to get the compression force on an area. So it's 0.85 f prime c times A times the width of the beam B. And that's what force PF C is. Where does that resultant act? The resultant act at the centroid of this area, which is the middle of it. Statics again. So if this is A, the resultant is A over 2 from the edge, and A over 2 from that edge. All right, any question on that? We're almost there. We're almost there deriving the equation. The equation is very simple, but I just wanted to see how it's coming. So what about this distance? This distance between C and T. What is that distance? I know the distance from the top to the T is D. And I know this is A minus A over 2. So don't you think the distance is D minus A over 2? Yeah. From C to T is D minus A over 2. Because from here to the bottom is D. I have to subtract that guy on that. So that's that. All right? Now, so what happened here? Remember in high school physics, when you had two parallel forces equal, because we know C equal to T because for equilibrium, two equal forces parallel, separated by a perpendicular distance, that forms a couple in high school. A couple. That couple equal to one of the forces times the perpendicular distance. So that couple equal T times D minus A over 2 or C times D minus A over 2. That's what we did in high school physics. In college, the same concept, we call it moment instead of couple. So the moment here is equal T times D minus over 2 or C times D minus over 2. All right? That's it, really. So let's do an example and you will see how easy it is. It says calculate the nominal flexural strength of the beam. So I have a beam like this, 24 inches deep, 14 inches wide, 9 bars. Again, I can get the area 3 inches square. And then distance from here to there is D21. This is 3 inches. That's all given. Okay? He's saying calculate the nominal flexural strength of the beam. How much moment can this beam carry? How much moment can this beam carry? All right? Calculate the nominal flexural strength of the beam. If the yield stress is 60,000, that's the Fy. That's what's going to make the steel yield, Fy. Okay? Because F is stress and yield is Y. And the strength of concrete is 3,000. All right? So how do we do that? There's our stress block compression structure, 0.85 F prime C. This is the depth of this stress block A equal beta 1 times C. Here he already put beta 1 is 0.85. Why? Because look at F prime C is 3,000. 3,000, it falls in here. F prime C less than 4,000, beta 1.85. Okay? So he put that 0.85 times C. This is T equal AS Fy. Okay. So the distance we said d minus a over 2. What is c equal? 0.85 f prime c a times b. Okay, we just said that right there. So now what happened? So first, calculate the tensile strength T and the compression force C. Now look at this. Can I calculate T? Very easy. Why? Because I know AS is 3 inches square. I know Fy. What is Fy? 60,000. He told me the steel is gonna yield at this amount. So T equal AS Fy. Sorry, AS Fy. AS is 3 inches square. Fy is 60 ksi. Watch for the units. Inches square is gonna cancel, so the answer is gonna be in kips. So T equal 180 kips. All right. What about A? A is equal to this. I just finished this equation. I'm gonna go to this equation. 0.85 F prime C A times B. So C equal 0.85 F prime C A times B. 0.85 is constant. F prime C is 3 KSI. Why is that? Because he told me the compressive strength of concrete is 3000 PSI. So F prime C is 3 KSI. 3000 PSI or 3 KSI? Sorry. What about A? A, I don't have it yet. Why is that? Look at A. A is equal 0.85 times C. I don't know C yet. Okay. Now, C sometimes is the middle of the section. But when this beam starts to bend and getting to the to ultimate, that neutral axis is gonna start shifting. So we cannot say it's h over 2. All right. So therefore, I'm gonna leave A as unknown. I'll leave A as unknown. And what is B? B is 14 inches right there. So this is equal 35.7 A. How am I gonna get A? I know for equilibrium, C equal to T. So I'm going to set C, this value, T, equal to this value. So look, determine A by equating T and C. Why do we equate them? Due to equilibrium. So I say 180 equal 35.7 A. Can you get A? Easy. 180 divided by that is 5.4 inches. See that? So what that means is the depth of the compression block is about 5 inches. All right. Go back to the problem. He's asking me to calculate the nominal flexural stress. So I get that. Step C. Before we do that, what is the moment? Remember I said the couple or the moment is equal one of the forces times the distance. So T times that. That's the moment capacity. Or C times that. All right? So let's calculate the moment arm. We call it D minus A over 2. Let's calculate this distance, D minus A over 2. So that is, D is what? 21. Why? Look at this. This dimension from top to the center line of the steel is always D. In any book in this country using ACI code, that value is D. And then the total height is H, and then the width is B. This is according to ACI. We cannot change those. So D is 21 minus A is 5.04 divided by 2. We just calculated A right here. Okay. And then I can solve for the Mn equal T times D minus A over 2. Or A times that. Same thing. C times that. Same thing. So what is T? 180. We just calculated T as 180. And then times D minus A over 2 is that, 18.48. So it's equal to this. But look at the units. This is kips inch. Because D is in inch, A is in inch, so it's going to be kips inch. So it's going to be, and then you divide over 12, it gives you kips. All right? That's the example. Any question on that? And notice that we said calculate the nominal moment, not the ultimate. Nominal mean the actual with no safety factors, no magnification factor, nothing. So that's it. See, I could have just from the beginning give you this equation. Mn equal T d minus A over 2 and solve it. But no, we went through the derivation so you know exactly where everything coming from. All right? Now, the same thing you can do here instead of this, you can say C times d minus A over 2. But most of the time we use T. Why is that? Look at C. C is this. I don't know A. Then if you want to get C, you have to get A and substitute it here to get C. But T is already there, so you're gonna get the same answer. You understand? So it's easier to use T, but you can if you and try it at home. Put 5.4 here. This is gonna get 180. Same question, same answer. Any question on that?
So the lowercase c, that's the distance from the top to the neutral axis, right?
Yes.
And
but sometimes the like I said, the neutral axis will shift. Remember, as the beam starts to crack, this neutral axis is going to start to shift up, getting away from the crack. But
okay,
if the
so we
beam
can't
is not
assume that that's going
cracked,
to be half of d.
I'm sorry.
We can't assume that that's going to be half of d.
No, you can half of D or half of H.
D when it's an ultimate stress.
No, you cannot do that. You have to calculate that.
Okay.
But when the beam is not cracked, it's half of H over 2. Remember, we did that before.
Got it. So that's the only time we can use geometry, when it's uncracked.
I'm sorry?
So the only time we can use the geometry of it is when it's uncracked?
Absolutely, yes. Good. Yes, that is true. If it's uncracked, then it's H over 2. If it's cracked, then you have to go through this process to find C.
Got it, thanks.
Okay, you're welcome. Because the neutral axis is gonna keep going up, because remember the concrete is we're losing the concrete, so it's gonna follow the solid concrete. All right, so that's that. So let's do a second example. 2.7. Calculate the nominal flexural strength of the beam if the yield stress of the beam is 60,000, again Fy, and the strength is 3,000. Same thing. The only thing they did is they change a cross section. All right. Now let me skip this for tonight. I'll come back to that. It's exactly the same thing. The only thing is we're gonna calculate the compression area, and we have to, because remember what we did here, we apply C at the centroid of that. Same thing here. We're gonna calculate this area and apply this T at the centroid. But we have to calculate the centroid of that. That's why let me skip it. I'll come back to that. Okay? I'll come back to this. Let me see what else we have here. Okay. Yeah. So we're almost done with this chapter. Let me see. So what I wanted to do here very quickly, while we have it everybody, so we don't have to repeat it 3 times. Remember when we did the slab, we said the slab thickness in my example came 8 inches. Okay, I don't show it here. Okay, 8 inches. So how do I get that? And then I'm gonna call that a preliminary design for slab. So my slab is like this. Remember, I have 1, 2, 3, 4, 5, 6 spans. Every span is 15 feet. So how do I know and I know we covered it, but I'm gonna repeat that. How do I know the thickness? There's this table from the ACI code that tells me the minimum thickness. Okay, minimum. You can be higher than that, but you cannot be lower than that. And the code tells us if you use this table, you calculate the thickness of your slab or the thickness of your beam, because look at this. I can calculate the solid slab thickness and I calculate the beam thickness, and we're going to use the same one. If you use these formulas to calculate the thickness of your slab, you don't have to worry about the deflection of that slab. It will meet the minimum deflection required. Okay? If you use this table to determine the dimension of the beam or this thickness, you don't have to worry about the deflection of the beam. That means this is on the conservative side. All right? So that's what we're going to do. Let's start with the slab. The first thing it says simply supported. Simply supported is when you only have one span. Or we have 5 spans. So that's not our column. One end continuous. Both ends continuous, and then cantilever. We know what a cantilever is, right? This is a cantilever. We don't have that. Cantilever is a balcony. Balcony sticking out. We don't have cantilever. We don't have simply supported. But we have one end continuous and both ends continuous. We have both of those. Why is that? Look at the slab here. Look at the edge slab. This end is discontinuous because there's no span next to it. It ends here. But what about this end of this span slab? Is continuous because it goes down. How about the other piece? Yes, discontinuous, continuous. So these two end slabs fall under one end continuous. So if I want to get the thickness of those end spans, what is the thickness? Solid one-way slab, which we're doing, it's L over 24. Okay, L over 24. So what's L over 24? Let's punch that. L over 24. My L is 15 feet, right? L is the span length. So 15 feet times 12 inches divided by 24. 7.5 inches. All right? 7.5 inches. So it's telling me if I make my end span 7.5 inches, then I don't have to worry about deflection. What about the other span? What about this? This span, this span, this span, that span, the interior ones. They have both ends continuous because on this side there's a span, slab, and on this side there's a span or slab, the same thing. So these are both ends continuous. So look at the table, both ends continuous is L over 28. So let's check that. What's L over 28? L is 15 times 12 divided by 28. It gives me 6.4 inches. So the code tells me the interior spans can be 6.4 inches, but the exterior span has to be 7.5 if I'm not going to worry about deflection. So am I going to do that? Am I going to make those 7.5 and these 6.4s? No. In real life, we're going to make it all the same thickness. Which thickness I'm going to use? I'm going to use the larger. So I'm going to pick the 7.5 and make it all the same thickness. All right? Because it's practical. You lay the form flat for the whole thing, and then when you finish it, you want it also flat, because when you put your tiles, you don't want to go up and down, right? So you make it the same thickness. And then in my example, I said instead of 7.5, oh look, I did it here. I had it done here. Instead of 7, and so look at this, 7.5 and 6.4. I ran it at 6.5. So I say choose 8. You can go with 7.5, no problem, but to make it easy and to make it more conservative, 8 inches. So this is how we select the slab thickness. Any question on that? I know somebody asked me that question in an email. Does that answer the question? Anybody have a question on that?
I have a question, Professor.
Yes.
Was there a reason why you chose your to use your L2 instead of your L1?
Which one? I'm sorry.
So like you know how you're using your 15 because you're
in the lab?
Yeah,
from the lab? Yes,
yeah, like
okay.
right here you're choosing like your L2 in your example is 30
Yes.
feet. So why did you
Yes.
choose that instead of along the so you're basically
Yes,
choosing along
yes.
the girder instead of along the beam?
I know. Can you wait until we switch to the lab? I'll answer it there because it's in that presentation.
Okay.
If you don't mind, I'll come back to that, huh?
Yes, thank you.
All right, thank you. But I know exactly what you're saying. So any question on this lab? And notice we call it preliminary design. This is something to start with. Things could change later, especially in beams and columns. So we always call them preliminary first. All right. What about the beam? Let's go for a beam size. When we did the DT beam, I said assume, forget the numbers, 14 by 28 or 12 by 16, whatever. So how did we come up with that? So this is what we're going to show you in here too. And you need to do those so you can do your projects. Here I took my beam, L equal 40, 40, 40, 40. And this is my cross section. It's going to be B, D from the steel up. AS is the area of steel, and then H is the depth. That's always going to be the case, guys, in any book in the US. If you go to another country, they might use different letters, but in the US, following the ACI code, that's always going to be the case. It doesn't matter which book you pick, because all the books written out there is based on ACI code. All right, so how do I determine the depth of that? I'm going to go to the same table. Instead of using the solid slab, I'm going to use the second line, beams, or ribbed one-way slab. Forget that for now. We are dealing with beams. Same thing. Is my beam simply supported? No. I have 4 spans. Is my beam cantilever? Is it balcony? No. One way and one end continuous and both ends continuous. So same thing. Look at this, the exterior beams. One end discontinuous, one end continuous. One end discontinuous, one end continuous. So that's one. So this one falls under the first column, one end continuous. What is the minimum? Look at this. Minimum thickness, H, right? That means this is the H for the beam. See that? Not the width, the H. And when we did the slab, look at the H. I defined it for you. Is the thickness. So it's telling me for one end continuous, which is this one, H is greater than or equal L over 18.5. Where did that come from? Right here, 18.5. So if I do 18.5, sorry. So L is 40 feet times 12 divided by 18.5. It gives me 26 inches. Approximately 26 inches this needs to be. If I make my beam 26 inches, I don't have to worry about deflection. All right? What about the second, this span, the inside ones, both ends continuous. So if you go to the table, both ends continuous, L is L over 21 is the minimum thickness. So I do L over 21. L is 40 times 12 divided by 21 is approximately 23 inches. Of course, our beam has to be the same dimension, same thing. You're not going to change the depth of the beam. So we're going to use the larger one. We're going to use 26 inches. So choose H equal 26 inches. What about the width? The table doesn't say anything about the width. See that? But a good practice, or as a preliminary design, that's why we call it preliminary, you can start by assuming the width equal half the depth. 26 inch should be what? 13 inches. But in design, in real life, we like even numbers. So 13, make it 14. So the preliminary size of my beam is 14 by 26. All right? So please, when you do your DT beam, follow this procedure to calculate the size of your beam. Any question on that? All right. So now you can size your beam and then your slab, and you can do your DT beam analysis. The only other thing we need to do, and very quickly we'll do it, is remember when we did the column loads, I assumed my columns to be 12 by 12 inches. 12 by 12. So how did I come up with that? And I told you that for this building, especially the corner columns, are going to be 12 by 12. But how do we come up with that? This is chapter 9 materials, but I want to cover it now. We'll come back to it, of course, so you can proceed with your project. I don't want to delay. For now, we're going to go ahead and use the equation. I'm going to give you the equation and just use it. But we're going to derive this equation when we get to chapter 9. So the equation tells me the ultimate load that this column can resist, P sub U, which is equal phi Pn, the nominal load times the phi, okay, equal this equation. Phi times 0.8 times 0.85 F prime C, Ag minus AST plus Fy times AST. That's the equation. We will derive it, okay? So what are those? Phi is 0.65 for tight columns. We call it tight columns because it's not a spiral. Sometimes we have a spiral steel inside, but here we only have hoops, we call them tile. We'll cover that more later. So for here, just use it 0.65. AG is the gross area of the column. If this is my column, is B times H, the cross section of it. The gross area is B times H, right there. AST is the area of the vertical steel. Remember, we're going to put vertical steel in the column. That's the area of the steel. Okay, if this is 6 number 9, every one of them is 1 inch. So that be AS equals 6 inches square. Okay, so let's do an example and you'll see how we calculate the size. Very easy. Let's say my P dead load is 130 kips. My P live load is 180. Okay, so when you put rebars in this in the concrete column, there's a ratio. How much steel do I have compared to the concrete ratio? If I take area of steel divided by area of concrete, that's gonna be my steel ratio. Usually in real life, your steel ratio is between, the code allows us 1 to 8%, but most of the time practically is 1 to 2%. So we're gonna initially assume 2% longitudinal steel. So meaning that if I take the volume of the concrete, 2% of that volume is steel. The other 98% is concrete. That's what it means. So we define that steel ratio as rho equal area of steel divided by area of concrete. Area of steel is AST divided by A sub G equals 0.02. That's the 2%. That's what this means. All right? So rho equal AST over B times H, because that's the area of the column. AST equal rho times AG. If I cross multiply, remember AST equal rho times BH, but what's BH is AG. So rho, it's right here, rho equal B times H. I said rho is 0.02, so AST equals 0.02 A sub G. All right? Just follow the numbers for now. Believe me, I'll derive it for you, no problem. And then, of course, F prime C is 4,000, Fy is 60,000. Just come to this equation and plug in the numbers. These are P dead load and P live load. I have to get P sub U, so I have to do 1.2 P dead load plus 1.6 live load. You saw that in structural analysis, remember the ultimate load. P 1.2 times P dead load is 130, 1.6 P live load is in 180 equal to that. So look at this, I have a P column loaded with a P sub U of 4 kips. What size this column has to be? So you go ahead to the equation. Phi Pn equal P sub U is equal to that formula. P sub U I just calculated 444. Phi is 0.65. 0.8 is constant. 0.85 is constant. F prime C is 4. Instead of carrying all these zeros, you might as well do 4 and 60. Be careful of the units. AG is AG. That's the gross area. I don't know the area of the column. I'm looking for that. AST, the area of steel, I don't know that. But I know there's a relation. AST equal 0.02 A sub G. So instead of AST, I'll put 0.02 A sub G. F sub Y is 60. AST is 0.02 AG. Look at this equation. One equation with one unknown. What is the unknown? A sub G. Can you solve for that? Yes. If you solve, AG equal 188 inches square. Now, if you want your column to be square, then you take the square root of this. If you take the square root of this, then your column is going to be 14 by 14. If you take close to 14 by 14, but if you take 14 by 14, the AG is going to be 196, greater than 188, right? So if you take the square root of 188, let's take that for just quickly here. So 188 square root is equal 13.7. So if I go 13.7 times 13.7, it gives me 188. But do I want to build a concrete beam that is 13.7? No, I'm going to make it 14. So I'll do 14 by 14, and that will give me that area, and that's that. See that? You just size the column to be square. Or you can do rectangular column. You can say, I don't want it 14 by 14. I want one dimension to be 12. What is the other dimension equal? So you say the area, you can put that as X and then equal to this, then you can solve. So 12 by 16 will give you an area of 192. As long as those are bigger than what's required, then. So your column either can be 12 by 16 or 14 by 4. Is that clear? So this is how we sized up the column to use in our load calculations for the columns. Any question? Any question on that? All right. If not, then we're it's 7 o'clock. We're done, and then I will assign, like I said, I will assign a homework. Let's see, we have 41 people in attendance, so that's good.
Professor,
Yes.
you're not taking attendance, right? Because I have a class right now, a different class.
Yeah, no, I know. That's why I don't want to take it because I'm sorry I delayed you already.
Okay.
All right, that's it. So thank you very much for bearing with me, and then I covered what I wanted to cover, so I feel good. And sorry about being late, but that's it for tonight. So I will send an email with the homework, okay? And have a good evening, guys. I'll see some of you at 7:10.